Hello, this is Brian Washburn, and what I'd like to do is give an introduction to solving differential equations numerically. Specifically, we're going to solve a first order ordinary differential equation using methods that are known as RungeKutta methods. Okay, so what I'm going to do here is I'm going to introduce the topic, and then I'm going to go over some code that's going to solve actually motion for a pendulum, which is actually a second order nonlinear ordinary differential equation. So let's first talk about the general problem. So let's first look at solving first orders, and then we'll talk about how we're going to solve a second order differential equation. So if you take a look, this is my generic form of my first order differential equation. I'm going to solve for what I want to know is x is a function of time, and I can always write a first order differential equation in the form dx dt equals some function, and that function may be a function of x and t. Okay, now I want to get a numerical solution. Okay, and so just like with any differential equation, I need, since it's the first order differential equation, one of the rules we talked about is I need one initial condition. So my initial condition is x at 0. I'm going to call that x naught, and I'm going to solve this. I have to solve this for a range of times. Remember, I'm not going to get an analytic solution. I got to get a numeric solution. So I'm going to have to pick a range from 0 to time t. All right. Now, since it is a numeric solution, I won't get a function. I'll get an array of numbers. So what I have to do is I can choose how many points I want to solve for. That number I'm going to call capital N. And in practice, it's going to be like 100 or 1,000, depending on the accuracy or precision we want. So since I know I want to solve from 0 to time t, capital T, I can define something called dt, where that's just t is the range from 0 to t, and I divide by the total number of points. Okay, so then say t was 1 second. Big T was 1 second, and I have 1,000, then delta T is 1,000th of a second, or 1 millisecond. Then I can set up an array of time values, and I start off, this is my first element, so that's my first element. We're just going to say it's 0. And then my second element is going to be, well, 1,000, if it's 1,000th, it's 1 millisecond later, then 2 milliseconds later, and such, and then eventually I get to 1 second. Okay. Now, we can set that array without doing any solutions to the differential equation. That just sets an array of time values. In the end, what we want to solve for is an array of x values. So x0, we know. That is my initial condition. What we don't know is x1, x2, all the way to the end. And in the end, we're going to get an array of x values for arrays of times. And once we have that, we've solved the problem. And we can plot that on a computer using, Python, what we're going to do. Okay, but so the main thing is to get this array. How are we going to do that? Okay, so we're going to use a method called fourth order RungeKutta. A RungeKutta method is basically it's treating, well, okay, let's go into it. So again, what is the problem is we know this initial condition, but how do we get the next point? And remember, x1 is x evaluated at t. Okay. Now let's make it a little bit more general. Say I know the ith value for x, which is x evaluated at I times delta t, or I is an integer. How do we get the next point? Okay. Well, what we can do is it's kind of like an extrapolation with a line. So my form for getting, so this is the next point. X of I plus 1 is going to equal to my initial point plus delta t times a slope. Okay, and that's just a linear approximation. Okay, now that is valid as long as delta t is small. So that's an important thing. Is if you solve a differential equation, your delta t's are too big, all right, then you're going to get incorrect solutions. And how do you get too big a delta t? Well, going back to here. Remember, t is my total range, n is my number of points. So say I only solve my differential equation with, say, 5 points. Well, that's going to give me a, say t is 1 and this is 5. Well, that's 1 over 5. That gives me a very coarse delta t. I don't want to do that. I want this to be a small number. Now I don't want it too small. For example, say t is 1 and n is equal to 1,000,000. Then this is going to be 1,000,000th of a second. And then my arrays have 1,000,000 numbers in it. You can do that. It's just going to be really slow for a computer to solve. So for most of the problems we're going to be doing, n is going to be on the order of 100. Okay, or sorry, 1,000, or maybe even 10,000. And that'll take less than a second of computational time to solve. Okay. So, again, what we're going to do is we want to get xi given xi plus 1 given xi. And we're going to use a linear slope to do that. Okay, now notice the slope is basically a time derivative of this function here. Well, we don't have a function. We have to represent that as a list of numbers. So how are we going to get this slope? So this is where the algebra gets a little complicated. You can basically, what RungeKutta does is expresses this in a Taylor expansion to fourth order. That's where the fourth order comes from. And let's take it. So this thing represents an average slope from a Taylor expansion. All right. Now the details are difficult and a little algebraic intense. I'm just going to show you the solution. Okay. All right, so basically, well, how do I get that average slope? Again, this is my average slope. My average slope has this form here. Okay, delta, this is the thing in the big brackets is the average slope, where these are the terms of that average slope. And that comes from a Taylor expansion. And I don't want to get into too much detail how you get these specific terms. Okay, and part of the reason why is because we're not going to write code, RungeKutta code. We're going to use existing RungeKutta code. I just want you to understand how it kind of works. Now, there is a visual representation of these terms here. Remember, this thing in brackets is an average slope. All right. So let me show you that in the next slide here. Okay, or a weighted slope. Okay, so you can identify these terms here from this expression here in this picture. This first term is the derivative of the function evaluated at ti. Okay, so that corresponds to, I didn't write it here, but this point right here. These guys here represent midpoint averages, so they're not at the midpoint, they're about the midpoint. Okay, remember, I don't really have a number here. I have a number here, I have a number here, but this is in between my numbers. Okay, and then this guy here represents a derivative or at the end point there. So then these terms here, 1, 2, 3, 4, those are my 4 terms, okay, represent the slope, okay. All right. So that's how fourth order RungeKutta works, okay. Now, back in, when I was an undergraduate, if we had to solve using RungeKutta, we would have to first write the RungeKutta code and then use that code to solve. Luckily, nowadays there exists packages that are forms of RungeKutta that are much better than anybody could ever write, or you could write, or myself could write. And so instead of doing that, just use that. I'm not going to write my own RungeKutta code. That's just dumb. All right, I'm going to use code that I know it works. Okay. However, there's still one more thing we have to worry about. All right. I mean, we don't want to solve a second. We do not want to solve a first order. We want to solve a second order differential equation. How the heck are we going to do that? Well, like we learned before, any second order differential equation can be written as two coupled first order differential equations. And that can be solved using a RungeKutta method. And the example we're going to do now is that of a simple pendulum without the small angle approximations. This is the differential equation I solved here, okay? And this is a second order ordinary nonlinear differential equation. There's no method on a piece of paper you can solve this differential equation. But what I'm going to do is I'm going to write this as two coupled first orders. I'm going to define omega. That is the angular frequency. The angular speed, I should say. All right. And then I can say, by doing that, then I get two coupled first order differential equations. Phi dot is equal to omega. Omega dot is equal to the rest of the stuff that's here. All right. I'm going to write this as a system of equations. Okay, I'm going to write this as y, where the first term in y is phi, the second term is omega. the rate of change of dy is going to be phi dot y dot, again, in this kind of column vector. It's going to equal omega and then omega naught. Again, remember, omega naught is the, just to remind yourself, omega naught is the natural frequency, and the natural frequency is equal to, well, in this case, it's the square root of g over L. Okay? Okay. Now, okay. All right, so like I mentioned before, is we're not going to write RungeKutta code. We're going to use tried and true existing RungeKutta code. And specifically, we're going to be using Python to do this. Now, you could do this in MATLAB or Mathematica. Python has some very nice packages. And we're going to use something called the ODE class from SciPy Optimize. So, before I'm going to now look at the code, okay? But before I look at the code, what I want you to do is pause this video and read from Canvas to PDFs, short PDFs. Read Computational Physics Worksheet 7 and Computational Worksheet 8. Computational Worksheet 7 talks about, gives a little bit more overview of the ODE class and solves it for quadratic error resistance, I believe, which is a problem we'll do in a little bit. And then Computational Physics Worksheet 8 goes over the code for solving a simple pendulum. Okay, so pause that, read that, and then come back. All right, and then I'm going to go over the Python code. All right, you paused it, right? Okay, right? Okay. Okay. Now, I assumed you paused and read those things. All right, I'm going to trust you. So now what I'm going to do is I'm going to look at the Python code I've written. Okay, so let's take a look at that. The code I'm going to look at, let's get rid of this guy, is Phys 522 simple pendulum. Okay, and I'm going to use Python to do that and explain how we're going to do this. All right, so I'm going to go through the code line by line. And remember, just to review, remember what we want to do is get solutions x as x in time. So we know the time values because we can set that, but we want to get an array of x values given an initial condition. All right. So how are we going to do this? Let's take a, first we're going to import packages that we use. First thing is we're going to use NumPy. NumPy is numerical functions in Python. Second thing we're going to integrate is this is from SciPy. We're going to use the ODE class, okay, to solve, and that sets up the RungeKutta differential equation solver. Second, we're going to load matplotlib to plot the results. I import an operating system and time features because the time feature is going to allow me to calculate CPU time. And then this line here, you should, if you have the code, and you should pull up the code while you're watching the video, okay? 522 is a module that I wrote. We're not going to use it right now, but it's going to be used for making little movies and stuff. Okay, and so what I'm going to do is I'm going to pull that up, and we'll use that in a little bit. Okay, so now what I do here is that line there starts the clock. I'm going to calculate the CPU time. Now, in these lines 22 through 27, what I'm going to do is I'm going to define parameters. G is the acceleration due to gravity. L is the length of the pendulum. Omega is the natural angular frequency. Natural frequency, again, square root of G over L. I calculate the frequency in hertz, and then the period, which is 1 over the frequency. Okay. Now, here's some text which explains what I'm going to do. All right, the differential equation I'm going to solve. Remember that my differential equation, going back to what I had here, was phi double dot is equal to minus omega naught, the natural frequency squared, times sine of phi. Okay, I'm going to express that into two first order coupled differential equations defining omega. All right, and so y is going to be my column vector of phi, then omega. And then so I can rewrite my equations as a system of equations. Dy dt is equal to a column vector, phi dot, omega dot. This is equal to that. That's equal to that. I need to do that in Python. Okay. So that's what this explains here. Again, I'm going to define, in Python, I'm going to define a variable called y. What is y? Y is an array of two numbers. The first number is going to be phi. The second number is going to be omega. Okay. And then I can rewrite my differential equation, and that's what I'm saying here. Y0, remember Python starts numbering from 0, then 1, then 2. So Y0 is the first element of Y. That's equal to phi. And then here I call it just d phi dt, or you can call it omega. Okay, Y1 is omega. So that's now I have my two system of this differential equation I have there. This is text. Okay, so now I have to write a function. dE is my functional form of my differential equation. Okay, and basically this is a numeric representation of this thing right here. Okay, so the first element of so dE is a function of time and y. The first element is equal to y1. That's basically saying dy0 is equal to y1. That's that guy there. The second element is dy1 dt is equal to this, which I put here, because that's my form of the differential equation. I have to write some form of the differential equation for Python to use. Okay, so Python is going to use this function de. All right. Okay. Now, going back to what I wrote before, remember, I have to get x as a function, all these x values. First, I need to set all the time values. All right. How do I do that? I do that by, I pick a number of points. That's my capital N, num. I pick some time range. Remember, I'm solving from 0 to capital T. Here, now what sets the time scale in the problem? Well, the natural period sets the, and so I'm just going to go 3 times the natural period. Okay. Then dt is going to be that time range divided by the natural, let's divide by the number of points. Okay. And then t is going to be the list of all time values. All right. Now I'm just going to run this really quick, but just let me say, okay, what is t? T is, t is not defined. Time range, so what's this? T0 is the natural frequency. That's 2 seconds. I picked the length of the pendulum, so the natural period is 2 seconds. All right. The time range is going to be 6 seconds. All right. Now, what is dt? dt is going to be, well, it's going to be 6 seconds divided by 500, and that's what I get there. So that's 12 milliseconds. Well, 12 milliseconds out of a total range of 6 seconds, that's fine enough. Now, 500 is a pretty small number, but it works. 1,000 would be better. All right. Okay. We set the time range. Now we have to set the initial conditions. A second order differential equation needs 2 initial conditions. The initial conditions are going to be the initial angle at time t equals 0, and the angular speed at time t equals 0. I'm going to take my pendulum and start at an angle of 10 degrees with respect to the vertical, and it's going to be, I'm going to let it go at rest. So 10 is the angle in degrees, but remember when we solve things, we have to convert to radians. This whole thing converts it to radians. The angular speed is 0, and then I just define y0. Remember, y0 is the angle. y00 is the angle at time t equals 0. y1 is the angular speed, and y10 is the angular speed at time t equals 0. Okay, I've set up my initial conditions. Now I have to set up arrays for the solution. Okay, my solutions are going to be, in this case, x or phi and omega. So here I have to define something. So basically I say y0. y0 is going to be the array of solutions of angles. y1 is going to be the array of solutions of angular speeds. I set it to a empty thing. This is called an empty set. I have to basically define it, and I have to say, here, have this thing here. I'm going to eventually set things to it, but eventually I got to define a variable. So this basically defines the variable, y0, y1, but there's nothing in it. Then this command here, remember y00 is a number, and then y0 append basically takes this number and puts it in the first element of that. Just put it there. All right. And the same thing for there. So when I have this done here, basically y0 is now an array with one element, the initial condition. Okay. Now I'm ready to solve the differential equation. I defined something called a backend. There are different types of RungeKutta solvers. Any of them will work for this. I happen to use something called DeltaT, and you can look into the SciPy webpage, understand what that is. I don't want to get into details, but there's different ways of solving it, but those are fine details. This will work. Now, the most important line of the code, or there's two important lines. This thing here, R is equal to ODE DE. What does that do? Remember, DE is a functional form of my differential equation. This ODE basically makes R of class ODE. And what is R going to be? R represents some thing that represents the differential equation. Okay? And so I give it the functional form, and R is of class ODE. If I just type in R here, and it says SciPy ODE, it's just something that represents a differential equation. And I can do things to that. Okay? So what do I do to it? First thing I do is R, the dot, and then set integrator. That says I'm going to solve my differential equation R with this DeltaT integrator. That's the method of RungeKutta I'm going to use. All right. The second thing I need to do is set the initial conditions. So this thing here says, okay, take R, set the initial values. The initial values are going to be the initial angular speed, and what times t equals 0, the initial time. All right. Next thing I'm going to do is in a loop, I'm going to solve for the differential equation. Remember, I have x0, so I need to get x1, x2, x3, blah, 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 and I need to do it for all elements. So tt is an element in my array of times. Now this thing here, notice I go from 1 to the parentheses. I'm going to start from not element 0, but element 1. Why? Because I know the solution of x at element 0. That's the initial condition. So I'm going to start from the next one, which is 1, element 1. Okay. This line here solves the differential equation at times tt. Okay. So if you looked at the array, tt, the first tt element would be delta t. The second one would be 2 delta t, 3 and 4, such and such. Sol is going to be an array 2 values. It's going to give me the solution of the angle and angular speed at times tt. Then what I do is I take Sol 0 is the angle, and I append it at times tt, and I append it to the solution array. This is the angular speed, I append it to the angular speed. And then I have some function here, if not successful, give me a problem. Okay? Remember, computers will always give you a number. Sometimes they're not right. It's nice to let you know that it's not right. All right, great. Now, these guys here are a type array. What I'm going to do in these lines here is just convert this to a NumPy array type, and that's just for plotting purposes. All right, so basically I'm going to convert y0, which is an array, to phi, which is a numpy array. Same thing with y1, and that's the angular speed there. All right. Now, for comparison, I know the solution for simple harmonic motion, and I'm going to write down the solutions for simple harmonic motion. All right. Okay, so let's solve. So what I'm going to do is I'm going to solve this equation for 10 degrees. Now 10 degrees is small, that is valid under the small angle approximation. So if I solve that, what I get is, see, the red line is the simple harmonic motion solution, the blue line is the pendulum solution, and notice that they're right on top of each other. That means that, so that's what I expect. For angles less than 20 degrees, I expect a pendulum to behave simple harmonic motion. Now, this phase-space plot, we're going to talk about this a little later when we talk about oscillations. But the thing you want to know about the phase-space plot is basically I'm plotting angle versus angular speed, or sorry, the other way around. If it's a closed shape, that means it has periodic motion. If it's a circle, that means it's simple harmonic motion. All right, so let's just leave it at that. Now let's do 20 degrees. I expect it to do, again, simple harmonic motion. And you can see there's a little separation. Okay. Let's do 30 degrees. And you can see here there's separation. There's some separation. So there's a difference between the simple harmonic solution and the pendulum solution. The other thing you're seeing is that the period of oscillation depends on the amplitude. That doesn't occur for the simple harmonic motion. That is a nonlinear behavior. Okay. In fact, one thing you can do is calculate the period as a function of angle. Okay. In fact, you did a studio for this in EP, and for simple harmonic motion, you showed that the period didn't depend on the amplitude, but for nonlinear motion, it does. Okay. And we can even do it in more. Let's do 50. You can see there's a large separation between that, and the period for the pendulum motion is getting longer than that compared to simple harmonic motion. Let's take it to the max. All right, let's do 90. You can see here that there's a big difference between simple harmonic motion solution, and the period is longer. So it's longer than it was before compared to that. Notice the phase-space plot is no longer circular. All right, so that's it. Now, one thing I do on the bottom, I didn't look at the code, but the rest of the code is plotting. This plots the angle as a function of time. This plots this phase-space diagram, which don't worry too much. We'll talk about what that is. Now, this guy here makes actually an animation of the plotting, of the motion, okay? And it uses a procedure that I wrote called make pendulum animation, which is part of Fizz. And what is Fizz? Fizz is a alias for this Physics 522 module. That Physics 522 module is a bunch of stuff I wrote basically for display purposes, and I put it in a separate module because I don't really want to explain. You can learn on your own how that works, but it's not necessary for you to understand how it works. You can just use it if you want. Now, what does it do? Well, what this specific module does, it makes an animation, okay, of the pendulum motion. Okay, so here I'm going to show you one of those movies, okay, and this is what comes out of it. And you can see here, sorry about that, is I picked some, I forgot what even angle I plotted. I think it was like 10 degrees. And you can see I get simple harmonic motion. It shows me the position of the pendulum as a function of time. Okay. Now what we can do next is do it for, say, a larger angle. Okay, so here what I'm going to do is I'm going to watch a movie of the pendulum for a larger angle. Okay. And this is 90 degrees. And you see the motion, okay? Now we're going to do this type of stuff throughout class. I know this is pretty boring, but say I have a double pendulum. All right, we can look at the motion. You guys want to see, we can do some, okay, sorry for getting cut off there, but, eventually what we're going to do is we're going to look at more complicated motion. So sometimes these movies are going to be kind of useful. One of the problems we're going to look at is a double pendulum. And for example, here is a possible mode of oscillation of a double pendulum. It's kind of cool. We can actually look at even more complicated or even chaotic behavior or nonlinear behavior of a double pendulum. So the ability to watch movies of the motion is actually going to be very helpful to interpret the physics of what's going on. Okay. So this is Brian Washburn. Again, what we've done was we showed you how to numerically solve the differential equation using Python, the ODE solver in Python, and we're going to be using this throughout the class. All right, thank you very much.